In this video, I want to show how you can fit the model of essentially parallel test score variables of classical test theory in Mplus. Oftentimes, when we run test analyses or other psychometric analyses, we're interested in fitting models of classical test theory to observe test score variables, and one model that we frequently use is the strictly parallel model of classical test theory. So we either use that explicitly by fitting it with confirmatory factor analysis, or implicitly by running an SPSS analysis, for example, an SPSS reliability analysis, and then looking at the Spearman-Brown coefficient, and so on. But unfortunately, the strictly parallel model of classical test theory often doesn't fit. And so I want to show you what you can do, or one alternative model that you can try when a strict parallel model doesn't fit. So this input file here is for the strictly parallel model of classical test theory. You can see in this model all the factor loadings are fixed to 1. All intercepts are fixed to 0. There's only one common mean. This is the parameter here, the tau, the factor mean. And then there's the tau factor variance, the true score variance parameter estimate, and then also there is a common error variance. So the error variances for the indicators are set equal under the model. So this model is the most simplistic model of classical test theory, where we only estimate 3 parameters: the common mean, the common true score variance, and the common error variance, regardless of how many observed variables we have. Now let's take a look at the output for the strictly parallel model for these 2 variables, see if it fits. And so obviously, I want to show you that it doesn't fit, and here you can see that. So the chi-square for this model is statistically significant. The model is rejected. The p-value is 0.0189, so that's smaller than a common alpha level of 0.05, so the model is rejected. Also, fans of approximate fit indices will find that the RMSEA is also a bit high, so that might be difficult to justify even if you don't believe in the chi-square so much, so that's also not so good looking. CFI and TLI look okay, but the SRMR is also a bit high. We want it to be usually around 0.05, and so this model doesn't really fit so well. Now, what is the reason oftentimes that the strict parallel model doesn't fit? Oftentimes the variables are not exactly equal in terms of their difficulty or mean. So here you can see the observed variable means, and you can see that the test score variable y3 had a mean of about 34, whereas the mean for y2 was only about 33. So on average, individuals got about one more point on the test score variable y3 as compared to y2. So this means that test 3, the second test here, was a little bit easier. And so the strictly parallel model does not like that. The strictly parallel model implies that test score variables have to have equal means. So in order to be strictly parallel, tests have to be equally difficult. Not just equally reliable, but also equally difficult. And so that is something that could be violated here. And so that's often the case when you have tests that differ in difficulty. Then the strictly parallel model will not fit. So what can you do in that case? You can relax that assumption about equal test difficulty. And how do you do that technically? You do that technically by estimating an intercept parameter for one of the 2 test score variables. So you use one test score variable as reference, for example y2, and so for y2 you might keep the intercept fixed at 0, but then for the next one and for any other, potentially for any other variables that you might have, you can freely estimate the intercept. And then you have a model that we call model of essentially parallel variables. So now the variables are no longer sharing exactly the same true score variable in the sense of classical test theory, but only essentially. So they share essentially the same true score in the sense that the true score variables for different tests can differ by an additive constant. So the true scores are shifted by the same constant for everybody between tests, and that takes into account mean differences between the tests, or in substantive terms, differences in test difficulty. So we're freeing up one of those intercepts with 2 tests. When you have more tests, you would potentially free up more of those. And then that additional parameter then gets estimated, and that's then an item difficulty or easiness parameter that takes into account the difference of the difficulty relative to the reference test, which here is now y2. So y2 is now the variable that defines the true score variable. So in that sense, this true score variable now is specific to y2. However, it's still a common true score because it's only a shift by a constant value. So we can still think of those true score variables for different tests as being perfectly positively correlated. They only differ by an additive constant. Okay, so that's called the model of essentially parallel variables, and that might fit, and that model still has some of the benefits of the strictly parallel model, as we will see. So let's take a look at what we get here in this for this model of essentially parallel variables in this simple example. I'm going to save this under a new name. I'll save this as essentially parallel. Now we can see the chi-square is not significant. We lose 1 degree of freedom because of that additional parameter, but we also get a very, very substantial drop in the chi-square to 0.845. Previously the chi-square was over 7, and that is a significant decline. You can see the p-value here is not significant, so this model fits well. The other fit statistics also look really good now. The RMSE is 0 and the SRMR is 0.05. Now, why is this model useful? Also because it has some of the benefits that the strictly parallel model has. For example, it has the benefit that the error variances are still constrained to be equal and the loadings are still constrained to be equal, and then as a result the variables still have equal reliabilities. You can see that from the R² output in Mplus, where they both have the same R², and in the sense of classical test theory, those R² values can be interpreted as the reliabilities for each of the two tests. So each test here, or each test score variable, I should say, has a reliability of 0.648, 64.8% of the variance in each test score variable represents true score variance. The remaining 35.2%, which you can see here under the standardized residual variances, are indicative of measurement error influences. Now, what does this additional parameter mean? So we estimated this additional intercept parameter that previously in the strictly parallel model was set to 0, and you can see that this parameter was estimated to be 0.79 and it's statistically significant. So it's significantly different from 0, and this means that the second, or the test Y3, or the test that underlies Y3, is significantly easier than Y2. That's exactly the mean difference. So this here, this parameter is exactly the difference. This is the mean of the first test, because now the true score variable is specific to y2, and so the mean also is equal to the mean of y2. It's no longer a common mean. This is now the specific mean for the reference variable y2, and so this gives us this shows us by how much the mean for y3 is larger than that true score mean that applies to y2. You can also see that again by looking at the observed means one more time. You can see that the y2 mean is 33.099, the y3 mean is 33.888, and so that's exactly the 0.79 difference within rounding error between those two means. So the intercept parameter is therefore an easiness parameter in the sense of test theory. So it tells you by how much the test y3 is easier than y2. I hope you found this video useful to learn a little bit more about classical test theory and the essentially parallel model and how to analyze it, for example, in Mplus. Please subscribe to this channel and check out the description for more workshops on psychometric, structural equation modeling, and other types of statistical models. And leave a comment in the comment section in case you have other topics that you would like to see discussed. And I'll see you next time.